Please join me in welcoming a world-leading expert in environmental remote sensing, Dr. Lucrecia Pettinari.
Thank you all for being here. So the idea of this presentation is to show you a little bit how remote sensing is helping us with the research of wildfires. And as Peter said, I'm part of the University of Alcalá Environmental Remote Sensing Research Group, which is this in Spanish, Grupo de Investigación en Teledetección Ambiental. And I've been working for the FireCCI project for more than 10 years. And to give you a background of the fire in the Earth system, actually fire is an integral part of Earth since the appearance of terrestrial plants for thousands of hundreds of years, million years. And since humans appear on Earth for more than 50,000 years, they've also started using fire for different applications. And as such, we cannot say that this is a new phenomenon. This has also always existed and always has shaped the ecological communities in many regions of the world. There are some ecological effects that we know about. For example, how plant species can develop specific traits to adapt to fires. For example, the Pinus canariensis in the Canary Island is a specific pinus that exists only there, and it was developed based on the conditions of volcanic activity and fires in the island, and it developed specific traits for that. There are other kind of plant species like eucalyptus and cistus and some pinus that they need fire actually to open the cones and release the seeds. And of course, for grass regeneration in savannas, fire has shaped the savannas with very quick return intervals of fires every year. And depending on the return interval of the fire, if it's every 100 years, every 10 years, every year, it's going to shape how the ecosystem works and what kind of species you can find. But apart of these ecological effects that we could consider natural in a way, the humans have changed these fire regimes. And this is where we are finding more problems when we think about fire and humans. There are other kinds of effects, of course. For example, the particulate matter and gases that are released by wildfires, that they have a lot of impacts, for example, on human health, especially. This is a photo from Kuala Lumpur, from the haze that you can get from fires. And of course, also all the gases released that contribute to climate change due to fires, when fires is a very important source of greenhouse gases. In the cases where we have fires in steep slopes, after the removal of the vegetation, the erosion increases. And if we have reservoirs that we need for water for the populations, they can also be affected by this siltation effect, and we can reduce the availability of water. And also it can have other kind of impacts, for example, on the changes of surface albedo in white areas that are covered by ice or snow. There's a group of people at the University of DTU. They just submitted a paper showing how the fires in 2023 in Canada, the carbon deposition in Greenland due to these fires contributed to an increase in the melt of the ice in Greenland. And the worst possible cases, of course, is where fires affect us directly, affecting our houses or infrastructures or any kind of assets. And the worst possible scenario when we have lives lost due to fires that can be either from firefighters or the general population that sometimes still have very big issues and die in some particular fires. We have to count dozens of people dead due to fires. So if we think about the fire cycle, before a fire, we want to assess what is the risk of a fire occurring. We want to see if we can prevent or at least try to reduce this risk. At the moment that the fire is occurring, the first most important thing is for the firefighters or the civil protection groups to respond to this fire. Maybe it's an area where they don't need to do any kind of action because it's a natural area that needs to burn to regenerate, for example. But if we have populations, towns, assets, or a protected area that we need to protect because it's very endemic, they have to respond and try to control this fire. After the fire, we need to assess what kind of impacts we had, and from that, try to adapt and reduce future fire risk. And in this talk, I'm going to focus in these two topics. I'm going to give you a couple of paintbrushes of ways in which remote sensing can help us to assess the risk, and then focus directly on the evaluation of impacts. We have finished last year an H2020 project called Fire Risk with a big group of people, 38 institutions, where the focus was to develop this conceptual framework of wildfire risk and see how we can, through this data, estimate the wildfire risk in a holistic way for the whole of Europe and try to decrease the risk. And through this graph that has a lot of things that compounds danger, the possibility, the propensity of a fire to occur, what are the assets that are going to be exposed, and what's the vulnerability of those assets. If we are talking about population, if we are talking about ecosystems that are very particular and need to have a special protection, I'm going to focus on two areas where remote sensing is specifically very useful and that we have worked in this project. And they have to do with fuels. When we talk about fuels, of course, we are talking about vegetation, which is what's going to burn. And we have worked on creating fuel maps for the whole of Europe, where first we did a classification. I'm sure, Richard, that these numbers, maybe they are not the same of yours, but they look familiar. And for this first classification, we use existing land cover maps, like the Corinne land cover, the CCI land cover, the Copernicus land cover, and some biophysical variables to estimate the fuel depth, the height of the vegetation, especially the surface vegetation, the grasses and shrublands, who are the ones who usually, the layer where the fire spread, and usually forest inventories don't have this information. But the most important thing in the use of remote sensing for this is that in order to input all this classification into a fire behavior model that's going to tell us what to expect from the fire, how rapidly it's going to spread, how much energy is expected to release, we need to have parameters for all these classes. And in the case of the canopy component, we have used, there's a PhD student that did her PhD in our department, focused on mapping canopy parameters based on GDI, on ALS, national forest inventories, and also using multispectral and SAR imagery to develop this kind of maps where we have all these parameters that we need for these models, like canopy height, canopy bulk density, canopy cover. And for this, remote sensing has been super, super important. The other parameter, the other thing that where remote sensing is very important is for fuel moisture characterization. For a fire to ignite and spread, the vegetation needs to be dry. If it's very moist, it's not going to burn. It's either not going to ignite or it's not going to spread. And when we have dead vegetation, for example, fallen leaves or dead grasses or small branches, only the weather information is going to give us the information of the fuel moisture. But when we are talking about living vegetation, the plants have different traits to retain water. And the way to know at a broad scale what is the content of moisture in that vegetation is through the use of remote sensing. As you can see in these reflectant curves, in the blue one, if you can see the color right, we have a typical vegetation spectral curve of some vegetation that is very moist. It has 123% of live fuel moisture content against the red one, which is drier with only 65%. And you can see that the near reflectance and the SWIR reflectance changes a lot. This is an example of a map that we created as part of this project for the 8th of March of 2023, based on Sentinel-3 imagery. And the way to do this is to first have a database of information of how are the reflectance curves of different grades of fuel moisture content that can be done either with laboratory studies or fieldwork, and then use radiative transfer models to model what would be what we would see from remote sensing, and then create lookup tables that allow us, once we have the image from Sentinel-3 in this case, to select the closest fuel moisture that we would find in that area. And now moving directly to impacts, and I did this on purpose to make it bigger because actually I'm going to be talking about during the fire in one part and after the fire in another way. There are two general ways in which we can detect the location and the extent of fires. One is through thermal anomalies that are usually also called active fires or hotspots. So I wanted to give you the three names because you will see it like that, like with all these different names. And also after the fire, we can estimate and create maps of burn area. In the case of active fires, the bands that are used the most are the middle infrared and the thermal infrared, these two, because you can see here, for example, this is from a paper of Wooster et al. Showing the algorithms for active fire detection from the Sentinel-3 SLSTR sensor, that this area in red is a pixel in a savanna where only 0.5% of the pixel is being burned, and it has a temperature higher than 1000 Kelvin, where the rest, the blue line, is the same savanna, but with a temperature of 300 Kelvin would be what we would have 25 degrees around that. So with these kind of algorithms using middle and thermal infrared, also help with shortwave infrared and some visible infrared, they can create algorithms to detect where these events of thermal anomalies are, and using thresholds, decide which pixel can be considered to be an active fire. Also, importantly for this, is that using the middle infrared, it's also possible to calculate the energy release of the fire with this term that is the fire radiative power. These are two formulas from two sensors, the Sentinel-3 SLSTR that I was telling you before, and the MTG FCI that I'm going to show you in a couple of slides. Some of the most well-known and most widely used active fire products are those derived from MODIS and from beers. MODIS on board of Terra and Aqua has been available since the end of 2000, but it's basically about to die and be decommissioned. But luckily, since 2012, also the beers sensor aboard 3 satellites in this moment. At first, it was Suomi MPP, and now also in NOAA 20 and NOAA 21, so we know that this is going to have a continuation. They are providing information on active fires, in the case of MODIS at 1 kilometer resolution, in the case of beers at 375, and for some bands at 750. So this is an image from the paper of Schroeder et al. Explaining this algorithm, showing the capability of beers against MODIS, Terra, and Aqua to detect these active fires as they are happening. And since a couple of years ago, for Europe and Africa, we have the 3rd generation of the Meteosat satellites. They are geostationary, and of course, they are only looking at this part of the globe. But they have a new sensor, the flexible combined imager, that has the capability of providing information in the infrared at 1 kilometer in the case of this part of the world, that is the high-resolution fast imagery mode, that is providing information at every 2.5 minutes over Europe. So we are reaching a near real-time observation of Europe. And every 10 minutes for the full disk. And with that, we can get things like this. This is an animation made by Andrea Meraner from UMETSAT, showing the fires of 2025 in the Iberian Peninsula, in Portugal, in northern Spain. You can see that both in daylight and nighttime, we can see the active fires. The different colors express the energy being released. You can see the plumes, the smoke plumes. And you will also see in a couple of seconds, hopefully, a big cloud covering this area and showing us that when we have a strong cloud cover, we also lost this signal. So we have information in near real time, but of course with some constraints. Here, for example. So if we have to cite some advantages of using active fires for fire detection, since they use thermal energy, they can detect the fires both during the day and night. And through the FRP, it provides us with information on the intensity of the fire. This intensity can then be related to the combustion completeness, what a proportion of the vegetation has been burned, and this can also be translated to emissions, how many gases and carbon emissions, for example, have been released by that fire. But of course, there are some challenges. In the case of polar satellites like MODIS and VIRS, for example, we can only see active fires at the moment of the overpass of the satellite. If when the satellite passes, the fire is not active, because it started 2 hours later, we will never know that there was a fire there. And of course, also the thermal anomalies can be confused with other things. For example, other sources of heat like gas flares, volcanoes, industries, some sources of thermal anomalies that are static. In that case, most of the algorithms already have a way to differentiate in between both, because, for example, MODIS and VIRS, they have an attribute in their data series where they have type, and we know that type 0 is presumed vegetation fire. So when we want to use active fires in our algorithms, we know that we have masked only for that, because we will have gas flares, we will have offshore flares, and other type of active fire information. Then going to the detection of burn area, just a quick recap of introduction to remote sensing. If you remember the reflectance curves, these are some typical reflectance curves of snow, of soil, of water, the typical curve of vegetation with the peak in the green and the near infrared and the lower vegetation in the sphere. And this is an example of a typical carbon signal after a fire. You can see, as before, that we have this big shift in the near infrared and in the sphere. And these are the bands that are going to help us, also both bands of sphere are going to help us when we want to design a burn area algorithm. This is a way of seeing graphically how we can see this fire. In this case, this is in one of the fires of 2023 in Eastern Canada. If we see an image with an RGB composite, we're going to see this, basically the smoke plume. But if we use a Swirl red composite, we are going to see the active fire. I don't know if you can see that they're very strong red, bright areas. Those are the flaming areas, the flaming pixels. And you also see that the terrain is a little bit more observable than before, because the SWIR band is more transparent to clouds. So it also helps us see more data. And here the burn scar is very little, but here you can see that after the fire, the burn scars can be differentiated because of this SWIR near change. So some typical algorithms to detect burn area use an analysis of the change before pre and post fire conditions. It can be either individual images or it can be composites of images. They can use either individual bands of the different sensors, or in most cases, they use spectral indices that are designed specifically for fire detection. And for those algorithms that want to create a data series that starts after the 2000s, when we already have MODIS, which was one of the first satellites providing very good information of active fires, the algorithms also usually include active fires to detect burn area, and I'm going to show you in the next slides how. And these are some of the most well-used indices, spectral indices, the normalized burn ratio, who uses near and SWIR to differentiate between burn and not burn pixels, MBR2 that uses both SWIR channels, the MIRI that also uses both SWIR channels, some previous algorithms using the red and near bands that were used for some satellites that didn't have SWIR information. And also more and more, they're being developed algorithms specific for some sensors. In this case, for example, BICE2 specifically for Sentinel-2, for example. But if you see, they are going to be using SWIR bands, near bands, and in this case, also some visible bands. So some advantages of detecting burn areas. Since the area and the burn signal persists after the fire, it's not like with the active fires that we don't see it when it's happening, we lose it. We can go and look for images after days or weeks after the fire, and we can detect the signal. But some of the challenges are that in some regions of the world, specifically in tropical regions, the vegetation regrowth is really fast, and we can lose that signal in a few weeks. And I will show you an example in the next slide. Also, of course, this is optical remote sensing and infrared, but persistent cloud cover can hamper the detection of these fires, and especially in areas who have a high cloud cover, for example, in tropical areas or in boreal regions. And there's also some other changes in land cover that are not due to fire, but they resemble it. For example, if we have harvesting, in the previous image we had vegetation, in the next image we don't. Or we have a flood. In the previous images we had vegetation, in the next one we don't, and the reflectance is very low. And for these kind of things is that active fires are very useful to help us discriminate between the two. And of course, cloud shadows can also be problematic, very problematic. This is an example in Central African Republic. Here is the site, where if you see that from November until March, this is a composite of images. We are reaching April, and the signal completely disappeared. So in 2-3 months, nothing happened. If we don't have enough images, cloud-free images, close to the day of the fire, we cannot go further than that because we lose the signal. The opposite case would be a boreal region where we have fires in July of 2024. Then this is, of course, winter. The next year, we can see still the scars, and we can go up to August and September of the next year, and we can still see the burn scars because the regeneration there is much slower. And of course, as the remote sensing Murphy law says that your study area will almost never be in one tile, or in this case, in one swath, and that is why you see these lines, and also the cloud cover, and I selected the ones with less cloud cover, because I wanted to show you that it is not easy. It's not very straightforward. We have to deal with a lot of issues. We have to deal with cloud cover. We have to deal with not having enough images of the days that we require. But that's life. That's why we work on this. And now I'm going to introduce you to some of the products that we have developed as part of the Climate Change Initiative FireCCI project funded by ESA. And these two products were developed at a medium resolution. The first one is called FireCCI 51, uses MODIS surface reflectance from MODIS Terra and hotspots also from MODIS. And we wanted to use only the bands that were available at 250 meters. So the information that we had available was near and red. And that's how we created the algorithm. And the time series of this data set goes from 2001 to 2022, because starting in 2022, the orbit of MODIS Terra started to shift, and then we considered that it was not very consistent with previous years, but at the same time, we have, since 2019, both Sentinel-3 A and B that also provide information almost daily, and in this case at 300 meters. So we developed a new algorithm, improved from the one before, using Sentinel-3 synergy images, and in this case, the SWIR bands, which are even better than the near bands for burnout detection, and BIRS active fires that I told you before, they have a better resolution and a better discrimination of active fires. So we provide information at this pixel resolution, the original resolution of the surface reflectance, but since we are working for the climate change initiative, our main users are climate modelers and climate researchers, and they want something at a coarser scale. So we also provide information at 0.25 degrees, which is easier to ingest directly into the models. I'm going to go very quickly through this algorithm of this data set. It was called previously FireCCI S311. Now we are in the process of renaming it Medium Resolution Burn Area 60 because we have transferred this algorithm from ESA FireCCI, which is more research, into the Copernicus Climate Change Service, which is more operational, and it's going to continue to be processed in that ecosystem. The algorithm basically uses MBR2 to create a separability surface. Here you see an image of how the MBR has a swift decrease at the moment of fire, so we have a high separability signal. And at the same time, it uses the active fires to create what are called spatiotemporal clusters, things like this, where we group the active fires that are located in the vicinity of each other and also in the same days, and say, okay, this is going to be a fire event. We are going to see what pixels of this separability index are below these active fires, and we are going to consider that these are the most probably burned pixels. And to extend this, we are going to select statistical values of the MBR and the separability of the pixels that we know that were burned and of pixels that we know that are not burned around that, the green areas here. And from that, it creates thresholds that it's not the same threshold for the whole tile that we are processing, that sometimes it can be problematic if, for example, in this case, that is between Angola and Namibia, we have at the top of the tile and at the bottom of the tile very different land covers. And then it's going to cause problems if we use one threshold only. But this algorithm is very nice because it creates thresholds for each individual patch that it's detecting. And the final stage of this is to grow from that initial pixels that we know that are very well identified as burned, a contextual growing to complete the fire patch using the thresholds that we have obtained. But what we provide to the users are what I told you before, the pixel product and the grid product. The pixel product is something like this. It's provided in GOT format in 6 continental tiles. And besides providing monthly burn area, this is an example of 2024, this is the whole year. We also provide information on the confidence level of the detection and also on the land cover that has burned. If this pixel is classified as burned, I'm going to tell you what land cover burned, so it makes it easy for you to analyze this data. This land cover information is taken from the CCI land cover project. And in the case of the grid product at 1/4 degree, the ancillary information that we provide was requested by our users in all these years since 2010 when this project started, and are of course the standard error because we always need to give an uncertainty information. The fraction of the burnable area in each grid cell, the fraction of observed area, it's not easy to see it here, but down there, it's below 100, which is the dark blue, because the users told that it's important to know if I'm not detecting fire here, it's because it didn't burn or because you didn't see this grid cell because it was cloudy all the month. So this is the information that we are providing. And also the sum of burn area per each of the land cover classes. This is a figure showing per month the global burn area detection by different products. MBR60, the one that I showed you the algorithm before, FireCCI 51, which was the previous one, the NASA standard product MCD64, and another data set that we created specifically for the Copernicus Climate Change Service, but now it's going to be replaced by MRBA 60. And this is an animation showing you how the monthly data looks. As you can see, there are things that are clearly visible. For example, in the tropical regions, especially in Africa, it's noticeable. The two seasons in the Northern Hemisphere from November to February, March, in the Southern Hemisphere from June, July to September. We can see, of course, the areas that burn in western India due to the burning after harvest of the two seasonal harvests in May and in October, for example. If we see it again, we are going to see the Black Summer there, the Black Summer fires in Australia. We can continue that. And these are medium resolution sensors. Then we started to produce, and these two were the first two data sets that we produced at high resolution. This fire SFD means small fire data sets that we created based on Sentinel-2, that means 20-meter resolution. The first one used MODIS active fires, and it was produced for 2016. The second one, version 2.0, was processed for 2019, which was the first year when we had both Sentinel-A and B, so we have double information every 5 days. And we also moved to BIRS active fires, so better active fires. And there's a paper by Chubieco et al. Showing that with this higher resolution, we are detecting much more burn area than the FireCCI 51 and MCD64. 80% more burn area for this area than FireCCI 51, more than 100% more burn area than the NASA product. And if we see a temporal series of global burn area, this is global detections around 5 million square kilometers. The blue line is FireCCI 51. This one starting in 2019 is MBR 60. And these two dots here are the ones corresponding to the sub-Saharan Africa. For sub-Saharan Africa, we are detecting the same, almost the same amount as for the whole globe for using medium resolution data. And why is this important? Because now we are actually getting to the point where we can see what is actually happening in the terrain. Before, with medium resolution satellites, we cannot observe the small patches, the agricultural areas, small burn patches. This research done by Van der Velde et al., they used different burn area products, calculated emissions, carbon monoxide emissions for the Southern Hemisphere Africa, and compared them to TROPOMI, which is the black line, TROPOMI emissions from carbon monoxide. And as you can see, the green line here is the emissions from the Sentinel-2 products. Finally, we are reaching the point where we are detecting what is actually happening. All this prompted us to create the first global Sentinel-2 dataset that we are finishing this week. Hopefully in a couple of weeks, we are going to send it to be published. So in a few weeks, when it's published, you can access it for free directly from the CCI website. It's called High Resolution Burn Area version 1.0. And so far, it's only processed for 2023. And the algorithm is the same, basically, as FireCCI SFD20. And since we are doing a pixel product at 20-meter resolution, we cannot provide continental tiles. It would be unmanageable. So the tiles can be downloaded in 5 by 5 degree chunks. Let's call it like that. And it has, of course, the Julian day of detection, the confidence level, and the land cover burned. But in this case, from the world cover dataset, that's a land cover dataset at 10-meter resolution. This is an example of a monthly time series for that year. The black pixels that you see there are cloud cover, and the stripe that you see there are the different swaths of the Sentinel sensor, because we are having information from different dates, so of course the clouds are not going to match. And in different colors, you can see the Julian day of the detection of the fire. This is an example of the pixel product. The grid product in this case is provided at 0.05 degrees. This is the complete year of 2023. But if we want to compare this to the medium resolution data sets, we transform it to 0.25 degrees. And then we compare this, which is the burn area detection from Sentinel-2, to the burn area detection of Sentinel-3. You can see the difference. And if we want to go and zoom in a specific area, we can zoom in to here, for example, Italy, southern Italy. This is the grid product for southern Italy. And if we zoom even more, this is what we see for a region around San Severo in Italy. All these patches are burned pixels compared to the medium resolution detections. You can see it's very, very different. And if we even zoom more, we can see the actual agricultural fields that have burned. And how are we in time? Okay, good. I'm going to finish the last 5 minutes with a couple of assessment of impacts of fires and see how remote sensing also help us for this. First, it's not directly an impact, but I'm going to introduce some characteristics of the fire of 2017 in Portugal that we are going to see later on after the coffee break in the tutorial, to which you are very invited. This is an image of 2017, June 14th, of central Portugal. Of course, clouds, but if you pay attention, you're going to see that here something has happened. If you go to a cloud-free image, you see this fire patch that it's called the Pedrogao Grande fire that burned from the 17th to 22 of June of 2017. It burned for more than 45,000 hectares. And it was a terrible fire for Portugal because 66 people died in that fire. And it was caused by an electric line. Of course, for something like this to happen, the environmental conditions need to be prone for this. It was a very dry summer. Those days had very high temperatures. The vegetation, the fuel moisture was extremely low, and that is what was conducive to all this. And it was a terrible summer, all the summer. So we continue to see images, and we continue to see more fires. More fires, October, and then from one day to the other, we see something like this. This is a cloud-free image. The 15th of October, more than 500 ignition points on the same day. In 10 hours, 244,000 hectares burned. We are talking about more than the size than the island of Tenerife in the Canary Islands. We are talking almost the size of Luxembourg in 10 hours. And terribly, 51 people lost their life in that fire. Apart from the dry conditions, there was something even worse that contributed to this, and was the Hurricane Ophelia that was coming on the Atlantic like this. And it brought winds to Portugal, not the rain, but the winds. So that is why you see all the burn scars like this, very elongated. Those are wind burn scars, wind-driven burn scars, all elongating and in the same direction. And it brought all the smoke from these fires to Spain, to France, to the UK. And to finalize, yes, one way in which remote sensing also helps us with other impacts. We can estimate the severity of the fire thanks to remote sensing, Again, using this spectral index normalized burn ratio, where we calculate the difference between the near and the SWIR bands. And when we have high values, when the near is higher than the SWIR, we know that the vegetation is in good conditions. When we have low values, we know that the vegetation is inexistent or it has burned. And we can calculate the delta between the pre-fire MBR and the post-fire MBR. And in the US Geological Survey, they designed these categorical classes to say high severity to low severity to not burn fires, where we can classify a fire scar like this and get maps like this. For example, this corresponds to a fire in Valencia, in Castellón, the northern part of the Valencian community in 2022. And we can have a classification of very severe, moderate severity, low severity, and this also can help us estimate the emissions from these fires and also help the foresters to see how they want to tackle the restoration efforts after the fire. So, to conclude, I hope that I convinced you that remote sensing is a very useful tool for fire research because it can give us information before the fire starts with some parameters for fire risk assessment. We can have information during and after the fire on the location and the size of the fires. It provides information for impacts of the different kinds of fires. And burn area mapping has a long history, a decades history of algorithms that have been improving on time with better research and, of course, also better sensors. And it's helping us find the true amount of burn area because the IPCC report a proportion of emissions due to fires with the fires obtained from medium resolution sensors. But now we know that the high resolution sensors show that actually the fire amount is much bigger, so probably the emissions have a stronger contribution. And of course, there's still room for improvement. And the challenge of processing large quantities of high resolution data is also something that needs to be tackled better. So with this, I am finishing my presentation, and thank you very much for being here. Thank you.
Thank you. That was a wonderful presentation. Question, boundaries. So you map all the different types of terrain I saw, but boundaries, whether they're man-made or natural, can also slow or even stop the spread of fire. Things like a river or a road or a wall, right? A wall could be made from wood and flammable or made from stone and not, right? So are you considering boundaries that run through all these different regions and the types and the widths of them, right? A small road, maybe a fire can jump over. A wide highway, it cannot, right?
Mm-hmm. What we do is create these maps that tell us where the fire occurred. But of course, the different fire breaks, that's another way of calling them, are going to be useful or not depending on the kind of fire. As you said, a road can be useful to stop a fire if you have a surface fire with low intensity that is burning grasses or low shrubs. But if you start thinking about forests or high winds, you are going to have firebrands, which will make it very easy for the fire and these firebrands, these leaves, for example, carried by the wind that are ignited, crossing the river, crossing the road, and especially if we have high fires. So they can help or not, depending on the conditions of how the fire is occurring. But that is not something that we are tackling in these maps. In these maps, for example, at 20-meter resolution, because at medium resolution, you won't see anything. But maybe at 20-meter resolution, you will see, and actually, when I was checking the results of the Sentinel-2, I saw some boundaries between fire and no fire with a straight line. What is this? And it was actually a road. But you can observe that when you have enough spatial resolution. If not, you cannot see it. Yes.
I have a question. We are looking at fires and we see a problem. Others can look at fires and see a solution. Have you thought of that? I'm meaning that a change of the fire pattern in a specific region, like the sub-Sahel area, might indicate that the farmers are moving from one place to the other due, for example, of a conflict. So if you manage to follow up the active fires, the patterns that are used by the years, you can see how sparse data providing areas can support assessments about what's going on in the political situation of a region. I don't know if you have seen that in your datasets, and these uses are of use for the potential users of yours.
I have not personally investigated this, but I remember about a paper from some years ago where they were studying the fire occurrence depending on the day of the week and linking that to the religion of the country. Because, for example, in a Muslim country, you won't have fires on Friday. And there were some kinds of analysis of this type. It's not what we usually do, but of course, there are things that can be done. And also, for example, you can see the way that the forest or the landscape is managed through these kind of fire maps, because, for example, I can see very big differences in a border of a country. If I go to China and if I go to Russia and I see the border of a country and there's fires on one side and not on the other. So it gives you some information of the forest management or the capacity of reaction, but it's not something that we have tackled in our group specifically. Yeah.
Yeah, I don't know, how do you sleep at night after knowing all this? But then I'm still learning about the whole thing, so I'm sorry if I just missed it. So you can see the minimum, what you can see is 20-meter resolution, yeah? What I missed is how fresh, how old is the data? Can I actually see real time and make real-time decisions? And if not, then when that's going to be possible, when we will be able to see 5-meter resolution?
Thank you. That's a very relevant question, and thank you very much for asking it. Our project, FireCCI, since the main users are climate researchers, they are not worried about near real time. They want the best possible product. And usually when you create near real time products, there are some drawbacks between the real time and the information that you have. For example, in our algorithms, we use 1 month of data before the fire and maybe 15 days before the fire to have all the information that we need for the best possible algorithm. We don't do this, but with the active fires from geostationary satellites, for example, the MTG that I showed you, we are reaching this point of having data every 10 minutes, for example. And also there are some systems. For Europe, it's EFIS, the European Forest Fires Information System. It has the website. And globally, GWIS, also from EFIS. And then from NASA, it's FIRMS. They have information almost in near real time of the active fires that are available. But if we are talking about polar satellites like MODIS or VIRS, we have observations just a few times a day, maybe 2 or 4. So it can be considered near real time, but maybe not real enough for the firefighter to know that there's a fire there and they have to go. But it's the best that it's available now. And now with the geostationary data sets, I think it's going to become more and more easier to get near real-time data.
I wanted to ask on top of that, because my mind went directly to EFIS. Is this going, or is it already connected to EFIS? And second question on top of that, EFIS is a restricted place, meaning the agencies from the states that have privileges to look at all the data are defined by the state. It's not that every user can use the data, the maps, all the maps of EFIS. What is the status that you're proposing, and what could be, let's say, adapted for these products and methods?
When you say that it's restricted, you are talking about downloading the data or seeing the data, because seeing the data, you can go to the website and it's perfectly free. You don't have to register and you see all that's available. But if you want to download, for example, fire patches, that is restricted due to confidentiality of the countries. So I had to ask for fire patches for Europe sometimes, and they provided me with some aggregated data per country, for example, or stuff like that. But it's true that due to constraints in data ownership, they are usually not providing the polygons, let's say, of the fire in a specific way. You can request it, but I think not for Europe. But if you want to see what's happening, you go to the website and you see the active fire information. And even you can see burn scars for Europe that they are computing originally from MODIS, now also from Sentinel-2. And you can see the burn scars there only for Europe, I think. I don't remember if GWIS has something like that. We are not providing this information because, as I told you, we are not working in real time. So, for example, now we just process 2025 of the Sentinel-3 products. So if you want near real time, that won't be helpful for you because our objective is another one. But in EFIS, you can see something very close to near real time.
Thank you.
One more question. Anyone who works in remote sensing can testify that clouds are very annoying.
Sorry, what's that again?
That clouds are very annoying, right? They obscure the area that you're interested in very often. You said that you had to account for them, but you didn't say how. So how do you adjust for clouds or other obscurities in the area that you're interested in?
In the medium resolution algorithm that I showed you before, what we do is create composites, monthly composites. So we take for each pixel the most clearest signal of burn. So we select the pixels that are not burnt. Let's say that are not cloudy. We are going to look days before and days after and create a composite that is not burned. That is not cloudy. In the case of the Sentinel-2 product, we select either we want to process this day, the 1st of July, and we are going to look 5 days before, 10 days before, and try to find the image that is less cloudy. But sometimes it's impossible, and a lot of omission errors happen because in the tropics or in boreal forest, you have months where you don't have clear observations. Or maybe the clear day is the one when the satellite did not pass because Sentinel-2, you don't have daily data. You have every 10 days with one Sentinel, every 5 with 2. When I was checking the results of this Sentinel-2, I was trying to find cloud-free data, and I had to go 2 months before or 2 months after, and we are never going to detect that because we are looking for the days around the day that we are processing and the active fires that we are processing.
How does that affect, you have infrared imagery and stuff as well, right? And clouds, they cast a shadow, they cool the area. So that also might mess with the temperature data that you're working with.
The shadows, more important than the cooling effect, is the surface reflectance signal because it's very similar to the ones of burn signal. So it's a problem. Most of the commission errors, as I told you about the omission errors, most of the commission errors come from cloudy pixels misclassified as burnt. But that is something that we have to live with in all the algorithms. We are doing the validation. An Italian team from CNR is doing the validation of this data set, so it's completely independent. This is something for the Sentinel-2. That is something that's still ongoing, so we don't have the results yet. And for the medium resolution sensors, they have also done the validation using Landsat and data. And we know that in medium resolution, we are detecting less burn area that actually happens. So the omission error is much higher than the commission. But it's the same in the same level of all the different global products. So that's what we have to do. We know, compared to Landsat, for example, that the medium resolution products, all of them, under-detect about 50% of what we can see with Landsat. And that is also one of the reasons why we decided to go to high resolution, in our case with Sentinel-2, and also we have done some tests with Landsat to try to decrease this omission error.
Just about appreciation.
Thank you. Thank you very much.